So I would like to begin by thanking the organizers, Axel, Eric, and Vadito for first enrolling us to the wonderful conference and then for inviting me here. And I would also like to thank the person for whom we are doing all this. Many happy returns of the day. We look forward to many such occasions. This work has been done with three people who were my students. Now they're all independent scientists: Vadito Mittal, Prasad Perlikar, and Shamriti Shankar Rai. And I'd like to acknowledge the support from those agencies. We've been working on time scales for various works for a long time. I will not go through everything here. I will concentrate mainly on two recent papers that we have written. One is on the persistence problem in two-dimensional fluid turbulence, and one is on dynamic multiscaling in two-dimensional turbulence. Again, given the nature of the audience, I'll probably skip details because all of you know these things. There are two types of problems I want to look at today. One is well known, I think, in the experimental literature, also the long residence time of tracers in vortical regions in two-dimensional flows. Let me remind you what that means. I can, I click on PLC. Yes, there we go. Alright, so here that black dot which you see there is a Lagrangian particle, and it has just got trapped in a vortical regime, and it stays there for a long time. Okay, I'm sorry. Okay, so that was the end of the movie. But that's basically what here now. How do I do this?
Click on this and
click on this.
Command L.
And I can do this. I think. Huh?
Command L.
L? Oh, command L. All right. Okay, good. All right. The other thing that I want to talk about, which is the second half of my talk, is to look at what, being an old critical phenomena person, I call a dynamic exponent. You can ask, what is the time scale tau sub L associated with a length scale L, and that should go as L to some power Z. If you do naive K41, you will say that's L divided by B sub L. This goes as L to the 1/3, therefore 2/3, and therefore ZK41 is 2/3. If you look at the sort of physics that goes into the Taylor hypothesis, then there is a mean flow, and therefore spatial separations can be made into temporal separations, and if I've got everything right, that implies a Z of 1, which I think is, if not explicitly, implicit in the work of Heisenberg and Unzaga. How do we bridge these two pictures, and what corrections do we have to make? Because of multiscaling, I will tell you as we go along. So here's the outline of my talk. I'll give you a quick overview of two-dimensional turbulence in subfilms, and then define the problem of persistence, at least in a way which I think has never been done before. Then I will look at multiscaling of structure functions and homogeneous isotropic turbulence. I'll go through this quickly. Much of this you know, but I will only concentrate on our recent results, and then there will be conclusions. Okay, two-dimensional turbulence in subfilms. Now here is an experimental picture from the group of Tabeling many years ago. This is of the sort that I just showed you from our simulation. So this is a Lagrangian tracer, and it goes around and around, but it often gets stuck in various places which are indicated by arrows here. And this is like that tracer which was stuck in the vortical region in the flow that I showed you. So how should we characterize this in some systematic way? And that is what I will tell you as I go along. So this all you know well. We want to study 2D turbulence, so those are the equations. Incompressible, you can write them in the vorticity stream functional language. You know the conservation laws, so all of you know these things, so I can skip this. Of course, you know that Creighton told us that there'll be an inverse cascade with a k to the minus 5/3 spectrum, k to the minus 3 forward cascade, and if we inject here. In the second part of the talk, when I talk about multiscaling, I'll be concentrating on this forward cascade. All right. Okay, the experimental systems we have in mind typically are electromagnetically forced soap films with a nice PhD thesis which describes details of such things. These are the types of soap films. It's suspended in a rectangular frame. You can force it in many ways by magnetic arrays and so on. These are typically low Mach number flows, and to leading order, again with the references, the soap film behavior is governed by the two-dimensional Navier-Stokes equation plus an air drag induced friction. Okay? So those are the equations we will simulate in our direct numerical simulation, which will be in this vorticity stream function formulation. If there are boundaries, we'll use no slip on the water stream.
So you don't have a Z component?
No, we don't have a Z component. No Z component.
And how is the soap film really 2D, two component as opposed to three component?
Okay, I'm not a real expert in that, but we can get into that. You're worrying about height fluctuations and so on, right? So as I said, in the parameter range where we have, there are old papers by Shoma, I hope that's how the name is pronounced, which actually tell you when this approximation is reasonable or not. And I will show you, since you asked these questions, that you do pretty well compared to experimental measurements of a variety of quantities.
Well, a soap film should be 100 nanometer thick, so
Yeah.
it's pretty 2D.
No, it is pretty 2D, but you can still ask the question, and she's right in asking it, and people have examined it at some level of detail. Okay, but I think it does reasonably well. All right, so you can study various things like the evolution of the energy, the dissipation rate with Ekman friction, viscosity, etc. You can study velocity and vorticity, structure functions. I will go over most of this quickly, except I will concentrate on certain topological properties of a so-called Okubo-Weiss parameter, which I will come to in a minute. So, we can do these things. I won't describe the details of the simulation. If you want details, I can give them to you after the talk. This is how the energy goes. This is the energy dissipation. I'm not concentrating on these quantities in the talk today. But you can measure structure functions. So this is just to tell you that we can do it. If you do not average circularly and so on, then you get some anisotropy. But you can average circularly, and we have done that. And you can do it both for the velocity and for the vorticity. And I will show you data for both of them.
What is pseudo color?
Yeah, it's all pseudo color. There is a color bar too. Okay.
It's called pseudo color. What is called pseudo?
Oh, you have to ask these. That's right. Yeah. I mean, it's the standard jargon of the graphics people. Okay. Okay, so you can get velocity structure functions. I show you here an ESS style plot, and from the slopes of such ESS style plots, you heard about them yesterday, you can get exponent ratios. Here zeta p divided by zeta 2, and we are quite careful. We look at local slopes, and so every number that I quote here for exponents will have error bars, which will be obtained by such local slope analysis.
That's direct cascade.
This is a direct cascade, yes.
Could you distinguish logarithmic corrections?
No, I don't think so. Vorticity structure functions show some multiscaling. You can't see it very well here, but believe me, there is some multiscaling. There are large error bars, but there is some curvature in this plot, and it is consistent with other people's data. And the velocity ones don't show any perceptible multiscale. What I will concentrate on today is this parameter, Okubo and Weiss. This is the velocity derivative matrix. For incompressible flows, this is 0, and you can write lambda in terms of omega squared and sigma squared. The important point, which was noted by Okubo first, and I guess then Weiss, is that lambda is...
The Weiss thing was actually done in the 80s.
Oh.
But it was a report of La Jolla, and everybody was quoting it, and eventually I said enough of that, and
you took it out.
all
Right.
I published it in Kubikadi.
Okay, good. So,
But Okubo was first.
Okubo was first, right. That's true. I mean, many people forget Okubo, but he was first. And at a point xy, if lambda is greater than 0, we have a center. If lambda is less than 0, we have a saddle. Okay, this is well known. strictly speaking, this is in the implicit limit, but even when you have viscosity and Ekman friction, it works pretty well. These are contours of the stream function overlaid on a pseudo-color plot of lambda, and you can see that lambda greater than 0 is centers, and lambda less than 0 is saddles. So it gives you a natural way of distinguishing between vortical regions and extensional regions. You can do PDFs of lambda. This is not the main purpose of my talk today, but I show it since you asked the question. And if you look at all the details, which I'm not going through, you will see that actually we get all the trends that are seen in experiments in soap films. So to that extent, this is a good description of soap films and experiments on those. Okay, there are some more details. But the main point, or one of the main points of my talk today, is to do the analog of a problem that is important in non-equilibrium statistical mechanics, which is called the persistence problem, which is defined as written here. Let phi of x comma t be some non-equilibrium field fluctuating in space and time. Persistence is simply the probability p0 of t that, or p of t, that at a fixed point in space, this quantity, the sign of this quantity, this minus its mean value, does not change in time up to the time t. Okay? And this has been studied for a variety of problems. For most problems you cannot get this analytically. For a very few you can. You can see that paper by Satyam Majumdar for the ones where you can do it analytically. And it is found that, at least in some cases, this probability has a power law dependence on tau for large tau, and beta is called the persistence exponent. So the question is, can we do this in fluid turbulence? And the claim is that at least for 2D fluid turbulence, we can do it in a very clean way by using this Okubo-Weiss parameter, which I have defined already. Because if it is positive or negative, then we have vortical or extensional regions. Okay? And this is just saying things that I have said earlier. So here is, again, a plot of this Lagrangian trajectory superimposed on one pseudo-color plot. The mean value of lambda is 0. We can ask now, how long does a Lagrangian particle stay in a region where lambda is greater than 0, that's a center, or where lambda is less than 0, that's a saddle? And how long then does the lambda field not change sign at a position x comma y? And that tells us how to handle persistence time of a center or a saddle. Okay? Now we distinguish between two types of persistence. One is Lagrangian, one is Eulerian. In the Lagrangian case, we follow NP particles and evaluate lambda along those trajectories. For the Eulerian case, we monitor the time evolution of lambda at a given point, and then we average over n positions in the simulation domain. For both cases, we find the time intervals tau over which lambda does not change sign. So then it becomes like a persistence problem, and we get these PDS of these intervals to characterize the analog of the persistence problem for two-dimensional turbulence. Okay, I have more details here, don't worry about them, but basically I have said all that I have to say. I mean, I can get an Eulerian PDF, plus stands for vertical and minus stands for extensional, so I can measure 4 PDFs, PE plus, PE minus, PL plus, and PL minus. Okay. There are simulation details, I can tell you more about them, but the simulation domains look small, the reason being that you really need very long runs in time to get good data for time-dependent quantities, so it's advantageous to stick to small simulation domains, but do good time averaging. Here's a plot of lambda for, you can't see this very well, the red is Lagrangian, the black is Eulerian, and you can see that, this is the sort of what the time series looks like. You can actually get autocorrelation functions, which I have not. Yes?
I'm sorry, this is a plot of lambda in a fixed position or
yes. For the Eulerian case, it's the fixed position. For the Lagrangian case, it is moving along with the Lagrangian particle.
Yeah, but this one, I do not understand. Where is the real, where is Lagrangian?
Sorry, so you can't see this. Red is Eulerian. If you were up here, I can show. There's color coded,
they're
but the
both
color is
shown
not
there.
Yes, they're both shown there, but they don't show up very well unless you look very hard. Like this is the black and this is the red.
Yeah.
Okay, I'm sorry, I should have drawn it better. Okay, so first let's look at persistence of a particle in a vortex. So this is the Lagrangian one in a vortex. So this is a log-log plot of a PDF. Okay, for the Lagrangian case, P L per S. They look like this. If you rescale all these times by their RMS values, they collapse onto one curve, which at least within this sort of statistics seems to be within our error bars. Our error bars are large here, independent of Reynolds number, injection scale, and Ekman friction, or just friction, I shouldn't call it Ekman. We have to extract the exponent. It is useful to look at the cumulative probability distribution. This is a log-log plot, so this avoids binning errors, and this is the region over which we fit. Don't worry about those lines, or something else. And actually there is a power, and this is the best we have been able to do with the error bars for that power. And then, of course, I hope somebody can do a better calculation than this. And the hope is that this will be a universal exponent as it is in other persistence problems. But at the moment, all we can say is independent of this, this, and this at the level of our simulation. Okay? But I think more work needs to be done. So this, I would say, is a clean definition of the persistence problem in 2D turbulence. If you look at all the other PDFs, the Eulerian ones and the Lagrangian one in the extensional region, they all actually have exponential tails from which you can fish out a time. But there really is no persistence side power law PDF. So this is a short summary of what I have just said. I can go over it later if you want, but there's no point to repeating this. Okay, the basic message is Lagrangian particle in a vortical region, power law PDF, from which you can extract a persistence exponent. Let me now quickly go to the second part of my talk, and with some luck I'll finish in 10 minutes so that we'll be back on schedule. Multi-scaling in fluid and passive scalar turbulence. Now, some of you are not critical phenomena people, except people like Itamar. In critical phenomena, when you are at a critical point, you look at, let us say, spin-spin correlation functions, and if you are at a critical point and R is a separation between the spins, there's a power law dependence, 1 over R to the D minus 2 plus eta. Please don't look at all this. This is just to get the critical phenomena right. Little t is temperature here, reduced temperature, not time. You can ask what happens if you look at space-time dependent correlation functions, and they also have a scaling behavior. Again, don't look at many years of history. For the purposes of this talk, all you need to remember is that the scaling behavior at a critical point is associated with a diverging correlation length psi, and associated with that diverging correlation length is the diverging time, which is related to this correlation length by what is called a dynamic scaling ansatz, and this defines the dynamic scaling exponent z. Right? Now, all of you know that there is a sort of intimate relationship between turbulence and critical phenomena insofar as the power laws we see in structure functions and inertial range are reminiscent of critical phenomena. And here are the analogs then of what we would call equal time exponents in critical phenomena. So here's the normal longitudinal velocity increment. You take it to its pth power, that's the order p structure function. If r is in the inertial range, we have this power, and that's the exponent. Okay, to get everything right, Kolmogorov dissipation scale, large length scale, etc. If the simple scaling, that's K41, this is P divided by 3, but as you all know well, experiments and simulations favor multi-scaling with zeta P, a nonlinear, convex, monotone increasing function of P. Now, so in critical phenomena, the transition from equal time correlation functions to time-dependent ones was made very rapidly. So why did we wait so long in turbulence? Well, because of some complications. One, which was implicit in my previous slide, has to do with the difference between Eulerian and Lagrangian. The point is, if you're in the Eulerian frame, if you do things naively, there will always be this sweeping effect which goes into the Taylor hypothesis. Therefore, temporal separations and spatial separations will be related linearly by the mean flow velocity, and therefore z, this dynamic exponent, will trivially be 1. And there are measurements due to Canada, etc., which show that. But if then you want to get rid of trivial mean flow type physics, you should go to a Lagrangian representation, and again there is some evidence due to Canada that you begin to see the 2/3, which I talked about in my first preview slide. That is, z would be 2/3. But it was pointed out, I think first by Belliniker and Lvov, that here is a good representation which you can use, which is called quasi-Lagrangian. Given any field, any Eulerian field psi, you can from it obtain the quasi-Lagrangian field by looking at the Eulerian field at the point r plus capital R, which is the position of a Lagrangian particle which at time t equals 0 was at the point r0, and this is also at time t. So formally this is the definition of a quasi-Lagrangian field. It is designed so that it gets out the mean flow. And suppose you had this, then the recommendation, I guess, in an old paper of Itamar, Lvov, and Podilov, that we should look at these order p time-dependent longitudinal structure functions. So what was just some delta u to the power of p is now p factors of delta u, strictly speaking at p different times. Just for simplicity for this talk and for our paper also, we take most of these to be 0, so only t1 is depending on time. Okay? Now, given such a structure function, you can extract from it time scales in many different ways. And again, for those of you who know the history of critical phenomena, no matter which way you fished out the time, the exponents did not depend on it. Amplitudes could depend on it, but not the exponents. But the richness of multiscaling is such that here, what exponents we get will depend on how we extract this time tau. So let us say I give you this structure function, this time-dependent structure function now. From it, let us say I give you some recipe for extracting a time, which depends on the order p. Then I will make this ansatz, tau goes as r to the zp, and from it extract zp. Now what are these mysterious different ways of extracting times? Oh, what happened here? No, don't worry, I just skipped over some stuff which I don't want to tell you now because of lack of time. One is an integral time. You take an integral over this time-dependent structure function divided by this. That will give you one set of dynamic multiscaling exponents from such an ansatz. You can also get times out of taking derivatives. For example, you take the mth derivative. You can check this as the dimensions of time. From it, you will get another dynamic exponent. Okay? And then if you generalize the multifractal model of Parisi and Frisch in a way, I guess, probably first done by Itamar, Lvov, and Podilov, you can show that there will be these types of so-called bridge relations. That is, the equal time exponents will be related linearly to the time, the dynamic exponents. Now we derived an analogous expression for the derivative ones. You can see they're different. Okay? And the question is, can you check them?
I mean, if the statistics is not intermittent, they should be.
Yes, exactly. Which I'm going to say in a minute. That if you if zeta p obey k41, you can check very quickly that everything becomes 2/3. That is independent of p. Absolutely. Okay, so this was. I will not go through the arguments because this was first checked in a shell model by Luca, Guido, Antonio, and Federico by using an exit time method, but the first checking with actual correlation functions was several papers from our group using shell models. I think I don't have the time to cover those, believe me that it worked out quite well. You know, these are time-dependent structure functions from which
You don't need any Lagrangian or quasi-Lagrangian.
no, because shell models, if you believe the ideology of the trade, are basically quasi-Lagrangian because of a technical reason that I can discuss later. Okay, so you can get log-log plots, etc. From it you can extract these times, and you can do it for the Creighton model where there is no time, no dynamic multi-scaling. But let me skip all that because that's not the main purpose of my talk today. Let me show you, so here are, you know, this is shell model data, and believe me, if you go through all the error bars and everything, the grid relations work. Question is, can you do it for a real turbulence? And so we thought we could do it well in 2D, okay? So this is a quasi-Lagrangian vorticity field, okay? As far as I know, this was the first quasi-Lagrangian calculation of a real flow. From it you can extract structure functions, from which you can extract these equal time exponents with error bars taken from local slopes. And then you can also get time-dependent quasi-Lagrangian structure functions, and from such log-log plots you can get the z's, again local slopes and error bars therefrom. And okay, let me skip this. So here's a plot of ZP versus P, which is integral. Open red circles the integral, blue circles are derivative. As far as I know, this is the first demonstration for an actual fluid thing, not just a shell model, where you see the clear difference between the integral and the derivative. And these are real error bars, as I said. So this is something that can be measured, and for once, I think theory is ahead of experiment, so it's a challenge to experimentalists to measure these. Here's a table with all the error bars. I won't bore you with it. So I think
this is all associated with small scales.
I'm sorry?
This is all associated with small scales.
Yes, small scale. Yes, absolutely. So here is a set of conclusions. We have calculated dynamic multi-scaling exponents so far only for shell models, but now we have it for 2D. Our work brings out clearly the need for an infinity of time scales and associated exponents, and linear bridge relations are satisfied. Okay, here it turns out even the Eulerian one, because of the friction, shows this thing. I can discuss that later. And about a month before we submitted our paper, Luca sent us this. They have done it for 3D, slightly differently, I think. Not exactly quasi-Lagrangian, but very close. So I can put up their paper if I can find it, and he can tell you all about it. Where is it? Huh? No, I don't want to trash it. I want to because they got into print a... Huh? Petronet. Okay. Sorry for the Bengali. Can you find this? Okay. Anyway, okay, thank you. I have to answer questions.
Preview it.
J'ai une question déjà.
Oh, une question, c'est bon. Fine.
Well, I will keep it in broken English.
Right.
In 2D, it is strongly believed that the dynamics is highly non-local, where you have most of the shear at scales much larger than those consideration. Now, this highly non-local effect, how pathological is it in its consequences for those dynamic scaling exponents?
Yes. So I should tell you what we did. We always had friction, which actually cuts it off. I showed you the speed of light, one thing where it cuts it off, and I mean, this is makes me sort of nervous saying it, but every calculation I know, including ours, supports it, that the k to the -3 exponent in the forward cascade seems to be k to the -3 plus delta, where delta depends in a non-universal way on the friction. So probably that is a partial answer to
No.
because the friction is cutting off those.
No, that's not what I mean. I mean that insofar as you want to maybe shed light also on three-dimensional dynamical scaling. Because two-dimensional, these particular two-dimensional things are quite pathological because of the highly non-local interaction. So,
I see.
Are you able to explain, for example, all those exponents in terms of things that don't differ too much from the linear, from the passive scalar model, where you prescribe the velocity field and worry about
The passive scalar, if you prescribe it with white noise, will not show dynamic multiscale.
Yeah.
Even though the
with white noise, but this is
yes,
not white.
right. This is not white. So okay.
Maybe I'll just, I don't know, maybe you will mend this. Let me put it extremely simple. In the direct cascade of 2D turbulence, the basic behavior of two particles which are close by is exponential separation, not power law. That's, in a sense, what you meant by non-local. If it comes from a large-scale velocities, and locally the difference of velocity scales linearly, well, it's actually logarithmic correction, but on a basic level, it's exponential. It's less exponential, but it's exponential. Which means that you aren't talking about exponents. The basic dynamics of two particles in 2D direct cascade is completely different from dynamics of Lagrangian particles in 3D, because it's exponential and not power law. The moment that you start to try to get exponents out of such multi-point, multi-time correlation function, you are actually having powers in distances and exponents in time, not powers in time, as you would have in critical phenomena. And it's very, very kind of dangerous, because you can somehow look for something which is exponent, which is just a log power law, but it is actually something which comes out of exponent. Direct cascade is very peculiar.
I'm not sure I
I
agree.
don't know. I mean, the data are in front of you.
And the faster the even if it's not k minus 3, even if it's even faster, it's even more close to exponential separation of particles.
These kind of measurements are really quasi-Lagrangian. You do not follow two particles separating.
Yeah.
The distance between the particles is kept fixed. You see, you just follow a sticker transported by one single particle. So it is a slightly different phenomenon.
So you keep this and you ask how other particles comes into these points which you keep the distance, bringing other values of velocity. The answer is exponential. Your velocity difference locally scales linearly with the distance, not like 1/3, and this is a huge difference. Your velocity difference between 2 points on average in a direct cascade scales linearly. And even if it's the scale which is larger than -3, even better, because it means that the first derivative of velocity exists on average. You see? Which means that it's locally smooth velocity field. So whatever you ask, how two particles separate, or how changes you know between other particles coming into this point, it is still locally quasi smooth field. And it's very different from anything else in turbulence.
Okay, maybe we can get back to that, but yeah.
Let me just change the subject to the decay exponents, or whatever we call it, the persistence
Yes.
exponent. But something I'm unclear, maybe you can help me put things in order. So basically, you're defining something in terms of plus or minus. It can be positive or negative, and you ask for the persistence time. Now that must have a very strong and peculiar system size dependence. Because when I look at system size dependence, I have plus and minus as I go to the center limit theorem, and I have to have something that goes like 1 over system size or 1 over square root system size or something. Now you didn't
Well, I
put the
mean,
system size
we
in this,
didn't
and I'm
do.
confused. I didn't read the paper of Satya, so I'm trying to understand
Yes.
what is the general statement, because there must be some system size dependence due to center limit theorem.
Okay, I have to look at
You
that
think
in
about this,
detail, but certainly we checked within our simulations bigger system sizes, and also here system size is called with Reynolds number. So we looked at different Reynolds numbers within our resolution. It doesn't seem to
Maybe
be
it's the coefficient that will depend, and not
possible.
the...
Yeah, but you know still.
But it's an interesting question.
No, absolutely interesting question. It's
I'm
just
just
that-
curious how it relates to center
Yeah,
limit theorem.
we should do much bigger simulations.
You know, Uma, that's?
I have just two comments on exactly this. I think Shukta's paper, they never talk about finite size dependence of exponent.
Right,
So I think that's why we completely missed it.
okay.
And in our case, if you increase the Reynolds number, the scaling range changes. The scaling over which you see this power law exponent,
Well, that's
that does change.
Yeah, that's normal.
No, that's normal.
Right.
Yes, but nothing more we have seen.
Yeah, so to the extent that we have checked, but we haven't done 32,000 square.
No, I'm just, it's a theoretic question, which I'm not clear about, and
Right.
which is interesting for me.
Yeah, we should, we also have other opportunities to discuss these topics, so maybe we should give Dario a chance to
Yes.
leave now.
Thank you very much.